Okay, today we're going to look at limits of accuracy, but this time we're looking at numbers that have previously been rounded to a given number of decimal places. You may have to look at the video entitled Limits of Accuracy to make sure you're familiar with this technique. So we're going to start with this first example. I've got 4.6 and we had a number that's been rounded to 4.6 to one decimal place. And I want to find the limits of accuracy, the upper and lower bound of what that number could have been. So I'm going to use the idea of a scale again. So it's been rounded to 4.6. The next one decimal place number would be 4.7. The previous one would be 4.5. Halfway between, it would round to 4.6 and stop rounding to 4.5. That would be at 4.55. Halfway between 4.6 and 4.7, it would stop rounding to 4.6 and start rounding to 4.7. That would be 4.65. We can use inequality signs as previously to show this in a really nice way. So 4.6 to one decimal place must have been greater than or equal to 4.55, but less than and not equal to 4.65. This is a really nice way of writing it, and it's often called the error interval. So if you ask for the error interval, that's how it should look. Second example, very similar, but this time I've got 3.72 and that's been rounded to two decimal places. So 3.72, the previous two decimal place number would be 3.71. The next two decimal place number will be 3.73. Once again, we look at this as a scale, and halfway between 3.71 and 3.72 will be 3.715. That's the lower bound. Halfway between 3.72 and 3.73 is 3.725. That's the upper bound. To write that as an error interval, 3.72 to two decimal places is greater than or equal to 3.715 and less than 3.725. Notice the lower and the upper bounds will have three decimal places when the number's been rounded to two decimal places. When the number's been rounded to one decimal place, the lower and the upper bounds will have two decimal places. And this is a pattern that will continue.